Hi everyone, we've come to the last exercise in chapter 10. It's going to be a bit different to our usual probability style questions because now we're going to show something special related to algebra that you can use combinations to apply. It's called Pascal's triangle. If you've been in Mr. Zhu's class, I may have shown you this once when we did polynomials. Now you're going to see exactly where Pascal's triangle comes from. If you weren't in this class, then be prepared because it's something very special. Our success criteria is can apply the binomial theorem to expand powers of a binomial. A binomial, by definition, is some pair of numbers placed together, either by addition or subtraction. Powers of a binomial means you're going to take the whole thing and raise it to a power. So the idea is there's a special theorem based on Pascal's triangle which you can apply to expand this very efficiently. So here is Pascal's triangle. We start with the number 1. That's our first line. Our second line will start with 1 and end with 1. The third line, it gets a bit more special. We're still going to start with 1. The next number comes from the result of adding the two numbers above it. So adding these two together, 1 plus 1, that gives us 2. Then we end in 1. I hope you can see why this starts and ends in 1, because if you did choose to add the numbers above the first or the last numbers, you're only ever going to have 1 and nothing plus 1 is 1. The next line is going to start once again with 1, then the next part will be the sum of the two numbers above, 1 plus 2 is 3, then 2 plus 1 is 3, and we end with 1. Next line, and this will be the last line that I'll draw. 1 plus 3 is 4, 3 plus 3 is 6, and 3 plus 1 is 4, and lastly we end with 1. This is Pascal's triangle. Here, once again, is Pascal's triangle. This is just an exact copy taken from your textbook. Pascal's triangle was developed by considering the possibilities when choosing from a small group of objects. Consider selecting from a group with one object. Let's call it A. You've got a book, it's A. How many ways can you choose it? Well, you've got 1, and you're going to choose, well, you can choose not to take it, right? That's an option. And the number of choices where you don't pick any object from a group of 1, there's only one way, not choose it. Well, what if you do choose it? How many ways are there? From a group of 1 object, you're going to choose 1. And there's only one way to pick a book, so it equals to 1. I'll point out right now, these ones, they're the same as these ones. We're actually building up our Pascal's triangle. I'll explain that one at the top in a moment. What we've got here is just a different way of writing the number of ways of choosing from a group with 1 object. To build the next line of Pascal's triangle, we consider selecting from a group with 2 objects, which are named A and B. Okay, well, from 2 objects, we can choose to choose nothing. How many ways is that? There's only one way to choose nothing. From 2 objects, we can also choose one of those 2. That means from A and B, I can pick A, or I can pick B. So there are 2 different ways. And lastly, how many ways can I pick both objects? If I'm going to take both objects, there's only one way to do it. Just take everything. So that's 1, 2, 1. Do you see where these numbers appear in Pascal's triangle? I'll point it out now. It's 1, which is here, 2, and 3. Amazing, isn't it? Okay, we're going to do one more line. So for the next line, it's about choosing from a group with 3 objects. So from 3 objects, it can be called A, B, and C. We're going to choose from the 3, nothing. How many ways is that? There's 1 way to choose nothing. 3, choose 1. Well, there are, if I'm only going to take one thing from the 3 objects, then there are 3 different ways. 3, choose 2. There are also 3 different ways. And, oops, running out of room. 3, choose 3. That's going to be only 1 way of taking everything from that group. You can probably see by now, it's 1, 3, 3, 1. 1, 3, 3, 1. So what's up with the number at the top? Well, this is asking, okay, it's going to sound really weird, but this group has no objects. How many different selections can you make? If your bag has nothing in there, how many ways can you select things? There's no way, because you can't take anything. So that's why at the top we've got that 1. Okay, let's link now the numbers that you get from Pascal's triangle, which are based on the number of combinations of things from a certain size of a group, to binomial expansion. So here are a few expanded results of variable binomial powers. And what's highlighted here in red are the coefficients. A plus b to the 0 is 1. Anything to the power of 0 is 1. Now, if you raise a plus b to the power of 1, you get 1a plus 1b. Because raising something to the power of 1 doesn't change that number, so it's still just a plus b. Raising it to the power of 2, we get the pattern hopefully you're by now familiar with, a squared plus 2ab plus b squared, and so on. Now I'm going to explain exactly how combinations can help us predict these numbers. And that's going to form the binomial theorem. Okay, now we're going to see what the binomial theorem is. We're going to do this by expanding a binomial, so we can see exactly how the coefficients of the expanded result are related to Pascal's triangle. And more specifically, how combinations actually predict the coefficients of your expanded form. So this example is a plus b to the power of 5. And first we write it out. Then we're going to start expanding this one by one. It's going to be very tedious. We're not actually going to do everything, but we're going to do the first couple, and then we're going to use the pattern that we see to predict all the others. Now, when we expand this is what we should see. We should see a set of terms where the first term is a to the power of 5. That's the result where if you're multiplying these brackets, you've chosen the a's each time. Now the number at the front, it's a bit blurry. This is C0, this is C1, this is C2, and so on. They represent coefficients. We call them C because we don't know what they are yet, but we're going to try and figure it out using some combinations. Let's think. The number of ways we can choose all these a's from the group of 5, there's only one possible way. That's just to take a every time you see it. The next coefficient would be C1. So this term is the result of adding together all the terms that you got where you've chosen A 4 times but only chosen B once. So what does that mean? Well, here's an example. You've chosen A here, 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 but not here. Here you've chosen B, which means you've got 4 A's and 1 B. That's one possible combination. Or you could have chosen A, then A, then A, then A, oops, A, then A, then A, then B, then A. It's another combination because in the second last one you've chosen a B and the last one you've chosen an A. Still 4 A's and 1 B. Obviously there's going to be a lot of combinations and we can use combinations to predict that. So all the different combinations are listed here. First, you could have chosen 4 A's and a B, or 3 A's and a B and another A, or 2 A's, B and double A, B, triple A, or B, then 4 A's. How many combinations are there? 1, 2, 3, 4, 5. That tells us that when we add together these like terms, there's going to be 5 of those. Okay, so the number of combinations gives you the coefficient. That's the result of adding together the like terms. Okay, just restating this, each of these terms comes from choosing A or B from each of the 5 brackets. There are 5 choose 1 ways of choosing exactly 1 B from the group of 5. So we're considering the fact that how many B's can we choose, because there's only 1 B in our second term. There's 5 possible B's, you only choose 1, and the result of choosing 1 B from 5 is equal to 5. That gives us the answer for our first coefficient. The remaining coefficients can be calculated in a similar way. Now we're thinking about the B's. In our second term, we're only choosing 1 B from the group of 5. In our third term, this is B squared, which implies that you've chosen 2 B's. How many ways are there to choose a pair of B's when there are 5 possible B's in total? Well, that's going to be the result of figuring out this question. 5 choose 2, it equals to 10. So there are 10 possible combinations where you've got 2 B's. And that'll be our coefficient of our third term. It'll be the coefficient because we've added all those like terms together. Same way for coefficient 3. Now we're choosing 3 B's from the total 5 B's. 5 choose 3, that's 10. Choosing 4 B's from the group of 5. 5 choose 4 is 5. And lastly, choosing 5 B's from the group of 5. 5 choose 5 is 1. Let's pause for a moment. I'm going to write one more up here. C0, which was choosing no B's. That's 1. I'm going to highlight this part. You've probably seen it already and just crying to shout it out. 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. They're the numbers in Pascal's triangle. And you can confirm that because it is about finding combinations when you're choosing certain numbers of things from a total group. Here's the binomial theorem. To expand a binomial raised to a certain power, you follow this rule. It looks complicated, but here's what you do. First, you raise the first term to the number of powers you have. So like a plus b to the power of 5. Okay, note that the first term has to be a to the power of 5. The coefficient equals 1 because there's only one way to choose 5 a's, or in other words, there's only one way of not choosing any b's. Then for the second term, when we're only choosing one b, we add together the like terms and find out how many there are by considering the combinations. So from a certain number of b's, which is given by the power of this binomial, we're only choosing 1. So that gives us the number of like terms. So the next term will mean that there's one less a to choose from and one more b. Here, we've got 2 b's to choose from. So from a total of n b's, we choose 2. We're going to have another one more less a, and we're going to have 2 b's. And it keeps on going. Every time your a power drops by 1 because you're choosing one less a, and your b power increases by 1 because you're choosing one more b. Until at the end, you've reached b to the power of n, which means out of n b's, you choose all of them and you don't choose any a's. By the way, the coefficient of that would be 1, because there's only one possible combination. Let's apply this now to an example. Example 8, expand a plus b to the power of 4. Now, to me personally, this formula is too complicated for me to try and remember. So I'm going to think about this logically. First, we're going to find the number of ways of choosing 4 A's, or in other words, no B's when there are 4 different groups. And I know there are 4 groups because it's raised to the power of 4. And I know that there's only one way of choosing all 4 of those A's to multiply. Next, we're going to choose how many ways of choosing 1B from the total of 4 groups. 4 choose 1. Which means we're going to have 1 less A and 1B in our term. Then, still considering choosing B's, now we're going to consider the case where we choose 2 B's. So from a group of 4, we choose 2. Which means there's another 1 less A that we have and 1 more B. You can probably see how this pattern's going, so let's finish up. Choosing 3 B's from a group of 4, which will mean we have A to the 1 times B to the 3. And lastly, choosing all possible B's from our group of 4. I'm just going to write B to the power of 4 because I only know there's one way to do it. All that's left now is to evaluate what these combinations are. So it's A to the 4 plus, there's 4 ways of choosing one object from a group of 4. 4, A cubed B. There's 6 ways of choosing 2 from 4. There are 4 ways of choosing 3 objects from 4. I can tell that there's only 4 ways because remember, 4 choose 3 is the same as 4 choose 1. So there are 4 ways. And lastly, we've got B to the 4. Okay, and that's fully expanded using the binomial theorem. And the binomial theorem's got to do with combinations. A thing to notice, you probably have already, 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. No one's going to stop you from just writing down Pascal's triangle and just subbing in these coefficients into your expanded result. So you don't lose marks if you don't write this part. But you need to show where you get these numbers from. So it's either writing down the combination notation, or, so this thing, or you need to reference Pascal's triangle. Okay, let's apply this to an example that's a bit more complicated. We need to expand 3 minus 2x all to the power of 4. So we have 3 to the 4 plus, now in the next term I'm only going to choose one of these 2 x's from the group of 4. 4 choose 1, where we have still 3 of these 3's remaining, and a minus 2x. And now we're going to add the fact that we're going to choose 2 of those minus 2x's. 4 choose 2, multiplied by 3 squared, because you've got 1 less 3, and you've got 1 more negative 2x. Now let's finish up this line. We're choosing 3 from the 4. We've got 1 less 3 and 1 more negative 2x. And lastly, we've got 4 choose 4, which means you're going to take all of the negative 2x's. And there's 4 of them. Okay, now it just becomes a matter of evaluating this. We have 3 to the 4, which is 81. 4 choose 1 is 4. 4 times 3 to the 3, that's 27. 4 times 27 is 108. 108 times 2 is 216, and you add a negative in front because it's a negative 2x. Negative 216x. Okay, moving on. 4 choose 2, which is 6, times 9, 54. 54 times 2 squared, which is 4. 54 times 4. I'm going to use that doubling trick. 54 doubled twice is 54, then 108, then 216. Okay, turns out to be the same. Plus 216x squared. I know it's plus because my negative sign is being squared, and I know my x is being squared because it's x squared. Okay, almost there. 4 choose 3. 4 choose 3 is 4. 4 times 3 is 12. 12 times 8. 12 times 8 is 96, if I am correct. Minus 96x to the 3. Minus, because we've got a negative sign raised to an odd power, and x is also raised to the power of 3. Lastly, we add 2 to the power of 4, which is 16x to the 4. Okay, we've got all the correct terms now. We just have to rearrange it. So the highest power of x is at the front. That gives us 16x to the 4. Take away 96x to the 3 plus 216x squared minus 216x plus 81. Okay, and in 3 lines, you've answered your question without having to resort to expanding again and again and again, because now you know combinations. Okay, once again, I'd like to remind you that your working out must show reference of combinations, or you must have Pascal's triangle somewhere on your page. It's got to be one of the two. Otherwise, if you don't include that, then I'm assuming you're pulling numbers out of nowhere. Unless you're doing a question that's pretty obvious, like this. If you're expanding this, then it's just a squared plus 2ab plus b squared. Okay, we've come up to the final part of the final bit, which is just reviewing our learning intentions. To relate combinations to Pascal's triangle and the binomial theorem, and can apply the binomial theorem to expand powers of the binomial. Once again, binomial theorem, just figuring out the number of ways we can choose b from a group of objects. And that's going to figure out how many like terms we have, which tells us the coefficient of that term once it's fully expanded out. This has been my favourite subject to teach because I love this. It's very logical, and once you learn it, it feels very powerful as well. It's like you want to teach it to someone else just so more people know about it. Okay, enough about that. I'd like to ask you now to complete the quiz questions just to check that you understand this fully. It's not easy, I admit, but doing these quiz questions will help you know whether you're ready or not. And if you're not ready, you know exactly which part you need help on.